Okay, we're going to look at a turnbuckle first of all. Let's see about getting this full screen. Very good. Um, Radius 5 millimeters, lead of 2 millimeters, L is 2 millimeters, R is 5. Coefficient of friction 0.25. What is the moment required to bring these two together? This is a picture of a turnbuckle. One of them's left-handed threads, one of them's right-handed threads. So when you turn this outer piece, the threads either move together or apart. So we're asking what happens if we move them apart. You'll notice the angles on the threads are different. 2 kilonewtons, 0.25 coefficient of friction. So there we go. You've got two of them going on. So you've got twice as much friction. Instead of the simple equation, if you have one and you're trying to bring them together, you have WR tangent theta plus phi. In this case, you have 2 WR tangent theta plus phi. W is 2,000 newtons. Tangent is phi, the coefficient, the angle of friction, is the inverse tangent of mu s, which is given by this. R equals 5 millimeters. L was what? 2 millimeters. There we go. Theta is 3.64 degrees. Plug and chug, ladies and gentlemen. The friction is bigger, 14 degrees, bigger than 3.64, so it will not unscrew by itself. Okay, belt and ropes, next topic. Used for power transmission. Friction is needed to prevent slipping. A timing belt, by the way, it has square teeth. It's a lot like a gear. And that is where you need precise timing. You want to absolutely guarantee no slip. If there is resistance, it's not a frictionless pulley anymore. So there will be differences in tension between the two sides, T1, T2, two different tensions as you go from one side of the wheel to the other. So we look at this free body diagram of a little increment of the belt right here. And we analyze that and we say, okay, T cosine d theta over 2, which is the projection along the x direction here, plus mu dn, there it is, there's force of friction right there, and the little arrow right here, mu dn, minus tension on the other side of this element, cosine, d theta over 2. Now, we can take the cosine of d theta over 2 to be approximately equal to 1. So this equation reduces to this. Mu dn, depending upon if it's static or kinetic, equals dt. Now, in the other direction, the y direction, here we have dn, that's the force acting on this element of a belt, minus t plus dt sine theta over 2, minus t sine d theta over 2 equals 0. You can take the sine equals the angle over 2, and you get dn equals t d theta. And you can solve. Eliminating dn, you can solve for dt, the change in tension over the tension, equals mu d theta. So every time you go along this belt, it depends on the angle, the contact angle between the belt and the wheel. You'll have a difference in tension. Okay. So let's look at a problem like this. The belt is in contact with two sides, A and C for 100, or B and C, excuse me, for 135 degrees. A is frictionless. So we're taking T2, or yeah, I'll give it a 2, T2. The tension here is equal to the tension here. That's fine. 135 degree contact angle. Now, we're given that the maximum tension is 500 newtons. So what's the maximum weight? Okay. Largest mass of the cylinder that can be lifted. That's what we're looking for. Coefficient of friction, 0.25. So we look at this wheel and we say, okay, what does T1 have to be? Well, it's just taking this equation. Mu s is 0.25, and beta is 135 degrees. You've got to convert it to radians, though. Okay. And solve for T1. Now, the next side, we're taking that value of T1. Now we're finding what the weight has to be. We're doing the same analysis, just doing the same thing. 153.9 newtons, 15.7 kilograms. So 50 newtons can lift 15 kilograms because of friction. You can't get more than that. Bearings, pivot bearings, discs, a clutch, a disc brake. I don't know why I wrote clutch twice. I should have written. There's another mistake in my my PowerPoint slides. This should be a journal bearing. No. Take that back. Thrust bearing. Wrong type of bearing. A thrust bearing prevents axial motion of the shaft, and this is a cone. This cone modification down here is an example of a thrust bearing. So you have F here, and you can think of it as applying to a ring at a constant radius around the disk. Okay? So F is mu dn. Well, here's dn. It's mu p dA, pressure. Little p for pressure, big P here for force. So force, big P, divided by the area. Well, the area is pi r2 squared minus pi r1 squared. So that's the total area right there. Big P over area gives you little p. Okay. dm caused by the force at this distance. You have to integrate it to get the total m. So r times this df will give you m. dA, that's what I was talking about, the ring. At a radius r. dA then is going to be the width of this circle times the circumference of the circle. Well, the width is little dr. It's differential r. So putting it all together, you get an integral that looks like this. Just algebra from here from this step to this step to this step to this step, algebra. And you're setting up the integral. And then finally, you're evaluating the integral at the end. These places where I put a yellow box are probably things you need to write down. The derivation, it's good that you understand how this is done, getting from here to here. But the final result is the one you'll probably use for problem solving. I mentioned that cosine alpha, that will tend, the normal force is going to be reduced by that, so you have an extra factor of cosine alpha in the denominator. If you have a cone instead of a disk. And of course, if you have two disks just against each other, then R1 equals 0. And you can get a moment. This is like a clutch. 2/3 mu times the force times, and then it becomes particularly simple. It's just R2 cubed over R2 squared, which is R2. So that's for a clutch. That's probably something I want to write down. So what are my two mistakes? Thrust bearing and clutch. Okay, I'm going to end the video here. We'll go on with problems, examples, stuff like that later.